Test, test.
Hello.
Hello, Crystal.
How are you?
It's very. Please try saying something.
Can you hear me?
Oh, now much better. Whew. Once I came to the meeting with seminar speaker right after the class, and it was like sequence, and I started this way, and they were joking. You can take it off. Virus is not transmitted through the computer. So you can start asking questions because how long will it take? I'm listening.
Okay. First off, for the magnetization value or for the J values I sent you. Okay, so we adjust the J values, and I understand that's the spin-spin interactions.
Hmm?
But when we're adjusting it like slightly, what does that like scale to? Like, okay, so are we adjusting how many are pointing up versus down, or how exactly does that adjusting correspond to the molecule?
Okay, so this parameter is not possible to change continuously for realistic models. So if you have molecule A, molecule B, they have very certain value of parameters of this parameter. So if you if you want to model a realistic material or a realistic, in addition to this ruthenium chloride planar sheet, there is a very broad area of molecular magnets when there are like like metal organic complex with two metals, for example. Hi, Tyler.
Hi.
So we already started discussing with Crystal, but you're welcome to participate. And so for each specific example of molecules or materials with magnetic interaction, this J value will be certain. So if you already have a sample in a beaker and you start making an experiment, you cannot change this parameter. You can change temperature and magnetic field, but you cannot change J. Why I was inviting everyone to explore positive, negative, and zero value of J? Because they are expected to show dramatic differences. It's different classes of materials. And why you are trying different values of small J, because you want to keep numerical stability on one hand, but describe J as close to zero as possible. But sorry, maybe you have questions. I'm talking too much.
Oh no, so you says is that we can't modify it and you get different classes of materials. So what are these different classes of materials that happen based on J? And when we're modifying it, are we adjusting like which ones are spins for like pairing to like adjust their spin-spin interactions, or what exactly are we adjusting for like in the molecule itself? Like, I know we can't adjust it in a real material, but what would be the difference between a material with like J equals 0.0025 versus 0.0005? Like how much of a factor am I changing it in like reality, and what am I doing?
I like your question very much. So the most popular materials are paramagnetics when J is close to zero, or when temperature is much bigger than J, when the thermalization of spins overrides their interaction. The mechanism for well, if we keep the same sign of the J but change the value of the J, so I'm not the strongest material scientist, so I will be just roughly telling what it is. Suppose you have a crystal of oxide, like aluminum oxide, okay, which like aluminum and oxygen, and then you replace each second aluminum with iron. Then there will be iron ions with noticeable unpaired spins, but they will be not closest to each other as in steel, but they will be spaced by oxygens and aluminum. Or we can take same model and tell like 1 iron per 100 atoms. Then distance between two nearest irons will be bigger, and their spin-spin interaction will be substantially deteriorated because of this distance.
Okay.
If you speak on the language of chemistry, for example, if you have a model, or not model, let me say, a material like metal organic complex with two metals, and by tweaking chemical synthesis, you can adjust size of the linker of the spacer molecule between them, and you can make them further away or closer, and it will change the J value. For opposite sign, how to make it opposite. If you have magnetic metals like bulk metal, like chromium, iron, they all will be ferromagnetic. The ions will be very close to each other. The spin-spin interaction will be drastically big. But if you take oxides, if you have dilute magnets, and especially if there are oxygens in between them, there is a mechanism where spin on metal induces changes in oxygen, and oxygen induces change of spin on the other. So this chain-wise interaction makes opposite spin antiferromagnetic more preferred. So it's a little deeper question to answer in more details, but basically if they are not tightly spaced, and if there is a second agent that makes this micro length induction, then this antiferromagnetism is possible. And in our case, this spacer is chlorines, like ruthenium, chlorine, ruthenium.
Okay, so we're lengthening the chlorine bonds then, or because I know you said it's ruthenium 3 chlorines and then 3 that are bridge, or are we? I know when I was reading on like some of the articles, they were saying that it's like stacked. Are we like adjusting like the chlorines this way for like, or are we adjusting the length of the individual bonds, or like the gap between the ruthenium chlorides?
Well, the attempt to change J is not a realistic experiment. I'm not telling that it is a wrong direction to do, but there is changing the value of a J corresponds to having samples of different materials and repeating the same experiment for different of them. I will answer phone call and we'll be back. We'll be back to you shortly. Oh. Okay, I apologize for interruption. Crystal, are you acquainted, are you aware of Marcus' theory of electron transfer?
No. Electron transfer. I can read about it though.
This year is not a part of our course, although it could be part of physical chemistry course. So this is quite famous theory practiced more by chemists and organic chemists rather than physical chemists. And there one takes, and Rudolf Marcus got Nobel Prize in 90s for the work that he published in 50s. So he predicts if the molecule or adsorption of two molecules in solution, which one is electron donor and other is electron acceptor, how quickly electron will go from donor to acceptor. And he has some parameters in some way similar to our J parameter, but he predicts dependence of rate on some couplings, and he makes a continuous curve. But in his theory, it doesn't mean that you take one molecule and tweak the bonds, make it longer or shorter or modify it. It means it's universal theory. One point on this curve will be each individual molecule. So same with J. By selecting different value of J, you are exploring different material if you are screening it. So I hope it was reasonable.
Yo, follow-up question. When I sent you them, I think the 0.005, because I know you said to look for when I have the heat capacity having a curve and that magnetization should be 1/T for when I look at the other graphs. But I think the 4 zeros and then the 5 was the like clearest graph. Is that the one you want me to adjust for the magnetization, or which one would you like me to adjust magnetization on? I can show you my graphs again.
Yeah, wait. I'll tell general things, and we should give also time to Tyler to speak. But let me make some disclaimers. I have clear mind. I just formulate the sentences. Okay. So one comment is DOS. Second comment is person. I'm willing and really starving to contribute to each individual project, and I'm really interested in your progress and success of the project. But nature of research, even mini research, means that it differs from regular homeworks and exams, that it is a problem that doesn't have answer, at least in big life. And it is a problem that doesn't have a adequately one and only one correct way of solving. So there is a lot of freedom, and it will be. I'll try to answer your question, but in philosophical, it will be not right for me to advise this or that value. So you just take the one that you think is reasonable here. So it's a little bit more freedom, a little bit more responsibility with our understanding that you are not left to swim alone in the ocean, but just try to guess something and go forward without asking. It's not that I'm declining to answer, it's just general philosophy. Second, density of states. By chopping the big problem, like divide and conquer, on different sections, I was trying to minimize effort of each individual contributor, so that, and in this sense, of course, you're welcome to do, like, duplicate what others are doing. But if you look more narrow on the subject that you selected, it's visualizing density of states and microstates and trying to do conclusions. So I really like that you run the whole code and check how magnetization and heat capacity behave and compare. But it's in some sense you're taking territory of what others will be doing. And I'll continue and listen to you. So as I imagine to myself your share of this project is to try to investigate how density of states depends on parameters, for example, on magnetic field. Try to identify the meaning of individual peaks and provide a fundamental understanding for speakers who will speak after you, so that they can refer to your findings. So if you do something that others are planning to do, it's good. and it will be backup if they fail. But looking on there is a thing that I have general idea how to do, but I do not have a ready to use code, and you can try to address this challenge. Like if you see density of states, you select a certain peak, and then how to represent, how to visualize this individual peak with spins ups and spin down. How to understand where is which, what is the nature of each peak, or maybe not each, but like a couple of representative peaks. And it will be helpful. I guess, and I have reasons to believe, that by changing the sign of J, one flips the curve upside down. So the all polarized moves from left to the right. But I haven't checked it. And this will be, if not a discovery, then an important step for future discoveries. Also, I guess very much that if you fix J and then start increasing magnetic field, then your this hump, this set of peaks will become broader and broader and broader. But so it will match Zeeman splitting vision for NMR and any magnetic field. But I haven't checked it. And even if it is a little trivial knowledge, it will be very strong pedagogical impact to the speakers who will speak after you. And because of graduate students are busiest people on the earth, they may not have time to check it and to think about it. So you will enlighten understanding of the whole class if you cover this subject. Okay, so sorry for speaking too much.
No.
Please ask your question.
Oh no, I wasn't checking like heat capacity and magnetization. Check that. It was just in class yesterday. You'd said to look to decide what value to use for J equals 0, since you can't use 0 itself. You said is to look until, because when I did that one, it was too small. And then you had told me just to look until that the heat capacity has a peak and the magnetization behaves as 1/T, and that's the J value I was supposed to use.
Okay.
So that's what I've been trying to figure out, and that's why I sent you all the graphs, was so I could find out what J value to use for 0.
I understand your logic. Yes. When I was one time I'm trying to do like each individual project out of this 9. When I was trying to do little test runs, I was using J just 100 times smaller than in class value. So instead of instead of 3 zeros, 1, I used like 5 zeros and 1. But again, it's all symbolic, and when temperature takes higher values, when we go to the, how to say, right wing of the graph, then thermalization mechanism will override any other interactions, will override magnetic interaction and override spin-spin interaction. So at substantially high thermal, all will be random, and magnetization will be 0, and heat capacity will approach 0. And on the other side, and it will relate to what we will discuss with Tyler, if magnetic field is excessively high, then magnetic interaction will override any thermal motion and any spin-spin interaction. So the code will converge and give numerically stable data. It's a little boring, but in these two limits, very high temperature and very high magnetic field, it will work with guarantee no matter what our J value. Whew. So anything else?
Yeah, just interpreting it a little bit, because I know John and I both had that same question. Oh, could I share the graph?
Yes, just a second. Let me make you both co-host. Oh, you're already sharing.
No, it doesn't let me share yet.
Oh. Co-host. Co-host. So you both are co-host and can share if needed. Okay.
Okay, so then this one would be, that's the really small one. Then you told me to use just 4 zeros and a 1, so I did that one. But if I go from like 4 zeros and a 1 up to 4 zeros and a 5, I get like a really nice distinct
Uh-huh.
2 gap. Because that's why I thought to use this one. That's why I was wondering if I was right to use that
The,
one and then change the magnetization on that one.
this is fine. And
then for this would be the ground state, right? This is what this core peak corresponds to. And from what I understand, this one corresponds to the maximum.
yes, correct. Maximum.
And then you said I'm supposed to pick peaks from in here and interpret them?
Yes. And it would be
How
really,
do you interpret ones within the blurb?
it will be really great if you could make this visualization of spins up and spin down for a couple of sample configurations. So you remember there is a way to show this honeycomb and just red and blue sticks protruding out of plane, right?
Yeah, for the first graph image that pops up for each of these.
So it is only one, but while computer is doing this simulation, he well, computer is not an alive creature, but in the computer processes like 20,000 configurations. It doesn't visualizes all of them, but out of this 20,000, you need maybe just 3 or 4 which are more representative, like first, last, and couple in between. So maybe you'll come up with more bright idea. I would do the following. I would, with already pre-made parameters at the beginning of the code, I would just pick the part that makes a random configuration. Then I would count magnetization, which show the, like, I will find magnetization and energy, not the energy for that configuration, and then look how does it relate with the x-axis of this DOS graph. So the energy will belong either to one of these peaks, and then I can do just place the image of this protruding sticks and connect it with line with the peak and tell, okay, this peak corresponds to this configuration. Make sense? As an idea.
Yes, the concept does. How to do it, I don't know what you mean for how to go about doing it.
So
I have had that open.
First, are you okay with the concept?
The concept, yes. The process, no.
This is normal. And we can try to fix it while speaking, or I can meditate in silence and just create a little video or just show recorded steps how I would do it. So you probably know that one can copy a fragment of a code and paste it in the command line, and then it will execute only that part of the code. So what if you identify the part of the code that creates random microstate, computes, so I think it will be like S vector, it will be saved. Let's not look on the code right now, let's just talk freely and go to details later if needed. And then there is a Ising Hamiltonian that is multiplied by this row and column, and then subtract magnetization times magnetic field. So the energy of microstate, I think it is called EMIC. So create microstate, compute EMIC, and then visualize this random microstate so that you already have this sticks protruding of the, and then take this EMIC microstate and look what is the value, how it relates to the x-axis of your density of states plot. And you can just make sense?
A little bit. More so when I actually try it, maybe?
Yeah, maybe let's make a plan that you'll try and then communicate success and or failure to me, and we'll try to fix it together.
So I'm gonna go copy out the part for the microstate part.
And maybe while you are trying, check with Tyler, because my time is limited. I need to go to different meeting in about 20 minutes. So, Crystal, please try. I'll talk to Tyler, and then we'll return back to your things. Tyler, I did send you example and 2 codes. Did you look on them?
Yes, I did.
Okay, so let's please express your questions right now, and then we'll go from there.
Okay. Thing is for the magnetic field response, in the code, am I only supposed to be changing the B value and the J value? Is that what I have to do, and observe what changes in the graphs?
I've got the question, and I do have an answer. I'm just very slow processing words into sentences. So we are practicing divide and conquer philosophy. Therefore, we chopped big problem on little assignments. And your assignment is for J bigger than positive, bigger than 0.
Yes.
So of course, you are very welcome to tweak any parameters and do any experiments. But according to original plan, it would be like, in my vision of what you would do, it would be to keep J unchanged completely. So do not touch J unless you have some reasons.
Okay.
Then in the version of the code that I sent to you, and I will send to the whole class as soon as I have a free minute, we screen through values of B, of magnetic field, instead of temperature. So in the codes that you have, magnetic field is changing. And if you look on the graphs that are plotted, x-axis is labeled like B divided by J. Magnetic field is on x-axis, not temperature, but magnetic field. Do you see it?
I do not see magnetic field changing in the code. To me, it looks the same. 0.001. Is it?
Oh, let me. Maybe I'll share a screen and show. And then
Okay, because I may be looking at the wrong thing, because I'm looking at line 3.
No. Let me share screen. So energy of, so this is E of B and second M of B. So one is showing energy as function of B, and another magnetization as function of B, and they are basically the same. Let me go to magnetization, because the results there are more interesting. It's less related to the class, but it's more beautiful in results. So the settings of the screening parameter is set in the, very close, I'm almost there, is set at lines 100 in this version, 100 and 101, and few next steps. So we take number of steps to be screened. AAA goes to screen them. Then we set scan is a non-linear scanning to have more denser points, grid points closer to 0. And then here we said originally we had temperature is some constants multiplied by scan. Now I have temperature fixed, it's not changing, but magnetic field is initial B naught multiplied by scan, which means as soon as we go through the code, the scan variable takes different values and B takes different values. Make sense?
Yeah, I believe so.
Okay, and let me bring, just because time is limited, I'll show it myself, although it will be better if you show and discuss. So here, when I try to practice this code myself, have you seen these images?
Yeah, I've seen them.
Okay, so see the x-axis is magnetic field, B divided by J. While in everything else we did in the class, x-axis was temperature, right? So now you see response of the system of the like magnetization and heat capacity to change of magnetic field. So if magnetic field is excessively high, then magnetization will be minus 16. So all spins will be oriented along magnetic field, no matter what is temperature and what are JJ couplings. And then when this magnetization changes at most, there is a peak or anti-peak in response of magnetization to B. This magnetic susceptibility is very broadly discussed in like Wikipedia and anything you read about magnetization. So for the energy, when we have zero magnetic field, the energy, and here is a positive J, the energy is close to zero. As even for because temperature is non-zero and they are randomly oriented. As soon as we increase magnetization, it drives all polarized down in energy, and average energy becomes smaller and smaller. So it's a response of total. Here is the wrong labeling. I apologize. I need to change it. It's not magnetization. It's total energy. So total energy decreases, and then we can take derivative of this. And at smaller values of magnetic field, there are some exotic and interesting things. But as soon as we go to high values of magnetic field, the energy, the derivative of energy in respect to field becomes constant. So basically, the larger magnetic field, the smaller the energy, and they are linearly connected. So what is your task is to try to rerun this code by, right now it's 900 Kelvin, but you can try like 100 or like 1 Kelvin or like 1500. Just select a couple of temperatures and do the same style of figures and share your observations.
So that's part of the code I need to change myself and no
Yes.
other part. Okay.
Yes. Only well, you're welcome. Like when kids play with new toys, they break it on pieces, right?
Yeah.
So you're welcome to do it with the code. But if you want minimalistic activity, just change this part of the code by modifying temperature and then let it do it work.
All right.
Whew. Any other questions from your side?
I don't have any at the moment. That helps a big question for me.
Okay. And the timeline, the schedule, so the written reports are due by last day of the class. I don't remember it from the top of the head, but it's Wednesday of the dead week, right? In class. So please bring, if you come in person to the class, bring 3 printed copies. Maybe
How long should the
I'll
report-
discuss it later, but have it
Okay.
fully done in week and a half. And presentations will be during finals week, when whatever is assigned day of exam, or we will just practice democracy and find the time that satisfies everyone. A presentation, just 5 minutes. Written report is about 4 pages. Well, 4 pages minimum, but if you want type more text, you're welcome, but shorter papers are easier to grade.
What all needs to be in the written report for 4 pages, or what all are we supposed to discuss?
Please repeat your question.
What all is supposed to be in the written report that's going to be those 4 pages? Like, what all do we need to type up?
Okay. On the 2 days before the papers are due, on the Monday, on the dead week, I will, for the whole hour of lecture, I will give very detailed explanation what to do. And I can, if you are interested, I can share to the whole class similar lecture, which I repeat in basically each class I teach. So how to populate reports. It should be, and I'll answer right now briefly. The report should mimic true scientific paper. Of course, it is mini research and mini paper. But as in any scientific paper, you have like introduction, which includes motivation, you have methods, you have results, and you have conclusions. So it should be a piece that is easy to digest and that makes a person who reads it happy. Not in the sense that it is all funny, but in the sense that it is logical, organized, and material is presented in digestible form.
So is the introduction just on our individual parts, or is it about the whole project, or what are we putting in said introductions?
Very right question. There is a little freedom, so you can blend both. Just tell why you think this ruthenium chloride is interesting in general, why Monte Carlo is why Monte Carlo is a unique method that nothing else can be done for this class of systems, and why specifically analysis of density of states will bring insights to anyone who studies this system, this class of problems.
Okay. Sounds good. I failed miserably. I found the line that I need, but not the like what to do, how to do from there. I think I found the line anyway.
So you have confused and discomfort about the procedure, how to do calculations or how to report them? What is the bigger confuse?
A little bit of both right now still.
Okay, but do not feel discomfortable. It's natural. I understand the level of discomfort for everyone, and there are no expectations of perfect works on one hand. On another, I do not know if it is what you wanted, but at least everyone voted for projects, and we are trying to mimic the realistic research life. And on one hand, people who do research are getting really inspired and excited because of this creative component and less pressure from people on one hand. On another hand, some people do not like research because it is too much freedom and too much and too less algorithmic rules what to do. So it is too much freedom and too much chances to do something wrong. So some people are discomfortable on that. But it is a nature of most of research project, because you are like warriors who fight sphere of unknown material. Like there is a sphere where we know things, how they connect to each other, and there is an out of sphere where materials we do not know what is outside and how concepts and objects are connected to each other. So it's like opening the door to the dark night and trying to highlight something with your flashlight. So it's just and probably most of you are already doing research for your graduate thesis, and it's not so big challenge, so big surprise. So it's just a little practice of doing same things that you are already doing and will be doing for your thesis. Do you feel a little bit more comfortable?
I'm still confused as to how to do the command line you told me to do though.
Okay, so I'm not sure if this if I will be able to fix it within the next few minutes, but
For within MATLAB.
Yes, within MATLAB. Let me try doing something and show it, but I apologize if I will need to disconnect because of the next meeting. Whew. Share screen. So let's identify the part that makes magnetization. So it's basically
If I'm right, it's like 230. Oh, no.
Well, this part is repeated here and there again and again. So random. So now I'm going here, pasting, and we have spin. Now I need to find the place where or the energy is found, and I think it is the same as E mic. It's repeated again and again. So minus 0.035. Now I can look for density of states and find on the x-axis where is this number. And I also need to just plot this one. There. Please. Rotate. So we have a microstate with number of unpaired spins equals 3. The energy is minus 0.03. The image is here, and I need to identify where is this energy on the image for density of states. So I probably have already closed the image with DOS, so I will redo it, but you do not need to do it because you already have it. So quickly screen. Yes. So this is image for very high magnetic field. So it is it looks a little bit differently what you did, because magnetic field is huge and it splits almost every level. And I need on this axis I need to identify the energy equals minus 0.3. So I can just maybe do the following. What E1 comma 2 comma O. I forgotten to do hold on. Let's do hold on.
Wait.
Hold on just a second. I'll fix it. Density of states once again. Okay. So you see, I just put it single point, showing that is it big enough to see?
Yeah.
Okay, so the state that we just draw, that we randomly created, this state will be corresponding to the peak right here. So a little to the left from 0.
Okay. And then what
and
did
it is
the
quite, just a second, and it is quite natural that it is here that number of unpaired spin is 3. So it is really close to 0. If it would be truly 0, it will be right above 0. And if I, of course, I'm not going to do it 20,000 times or even 10 times. I'll do like representative, the one for, I will do a couple of times and put them near different places and then make a visualization. So here is my DOS, and here are the states that correspond to this peak. And it seems quite helpful in interpreting results, not only for you, but for everyone who speaks after you.
What does the 2.5 represent?
I'm just looked on this figure and decided to plot one point. So I look here, the dot in the logarithmic scale goes like between 0.5 and 3, and I decided to put one circle where x coordinate will be equals to this E1 value that I completed before, and then on the y-axis I just voluntarily select something here like 2 or 2.5. I can do 3 and make maybe black dot. So they just a symbol on this with this x value.
Okay. Gotcha. So it's the energy that we calculated, where you want it up and down on the x value.
Mm-hmm.
And then what does the O stand for?
Or make a circle.
Okay.
I can do like multiply symbol star, then it will you can erase previous one. Delete, delete, and now I can do star. So you see it's a little star.
Oh, yeah.
So there are several symbols available, and one can either modify them in command line, or there are ways to modify it in the there are ways to modify the symbol, like select different symbol, make it like ugly big, make it maybe with a thick line, and then it just shows a symbol. Well, it just little tricks how to operate MATLAB. You probably it has nothing to do with science, just how to make the images beautiful. And you probably already did. If you click on this axis, one can change font to bigger, and the line can be, you can click on the line. One can make it thicker and maybe introduce dashes or dots so that it will be distinguished from others. But it's just little visualization things. My next meeting is starting, so any quick questions? Tyler?
No, I think that's it for now. Thank you. Helping me get started at least.
Excellent, excellent. Whew. Then I'll disconnect in a minute. And
one last quick question. I know originally you said you were going to send out some papers we could read, especially if we got to write an introduction. Are you still going to send out some relevant papers?
I plan to do it. I plan to do it, and it is. I haven't done it yet, not because I'm lazy or neglecting or forgotten my word. It isn't partially intentional. So I do not want reading to distract you from doing. It's more healthy to do first, read second. Okay, I need to finish.
Okay, thank you.
Thank you. Bye now.